Hello, I am Professor Stephen Abbott. Welcome to the fourth and final video in IGC, Inverse Gas Chromatography, what it is, what it does, via apps. As before, I acknowledge the help of scientists in the preparation of these apps and these videos. The apps are available on my practical chromatography website and they're all free. As a quick reminder, C has a column, like a GC column, and in this case we've got it packed with an inert support, and around that inert support is a polymer or oligomer or excipient, something we want to measure the Hansen solubility parameters of, and we inject a set of probe molecules and we measure how long each molecule takes to get through. Molecules which has a great attraction for the material on the support will take a much longer time to come out, other things being equal, than molecules with a low attraction. So by looking at the retention time and correcting for other factors like vapor pressure, mass, etc., you can get a measure of the affinity of a probe for the polymer, excipient, or whatever. And we'll show that we can take those calculated affinities and estimate the HSP of the probe material. Let's go straight to the app. So here's the app. It explains a bit about Hansen solubility parameters, where we want to measure DD, the dispersion, DP, the polar, and DH, the hydrogen bonding component. The classic way of doing this with solid polymers is to take a bunch of test tubes, put a bit of the polymer into each tube, add a solvent, and you'll find that the polymer is soluble in some solvents and insoluble in other solvents, and from that pattern of solubility and insolubility you can actually calculate the HSP. This works very well for solids, but is not so good for oligomers or excipients. So for these, C turns out to be ideal, as long as their vapor pressure isn't too high, so as long as they can survive on a column without being blown away by the carrier gas, you can measure the HSP. So what we do is measure the G, the specific retention volume, that's been discussed in the previous videos, so that clearly from the retention time. And then via this rather complicated equation we can calculate the thermodynamics of the interaction, the Flory-Huggins chi parameter. The inputs are the mass, the vapor pressure, the density and the molar volume of the probe molecule, plus B11, which is the second virial coefficient. These values are all known for the standard probes, and in fact in the app all those are available behind the scenes. You also need to know the density and molar volume of the test material. So you measure the retention time, you calculate VG, and then from this equation you calculate chi. Right, but how does that help us measure HSP? Well, the classic equation for HSP is that the distance in HSP terms is the sum of the squares of the differences between the DD, DP and DH value. And it happens that D squared is related to the chi value via this formula. So we know the chi's, we know the D of P and H values of each of our probes. So what we do is find values of D1, P1 and H1 for the polymer so that the D squared values fit the chi values. In other words, we do a least square fitting between calculated chi value from the estimated HSP value and the experimental values. This will make more sense when I show the app. Here we have the VG value of a number of probe molecules against a real polymer. This happens to be polycaprolactone, and we have a big list of solvents here. Where there's a 0, those solvents were not used as probes, and where there is a value, they were really used as probes in the experiment. And we have the density of the material we're measuring, we have a molar volume, and we have the experimental chi values going from a negative, which in principle is impossible but it seems to be quite common, up to something like 2, where there's a very big difference between the probe molecule and this polymer. Then we have a guesstimate of the P and H value for that polymer. And this is clearly an awful guesstimate because the correlation is very weak to the human eye, but also the R squared is only 0.46. So let's play around. Now, obviously in reality you would use a proper least squares fitting, but it's useful to build up an intuition. As I increase DD, things seem to be getting a bit better. As I decrease DP, things seem to be getting a bit better. And as I decrease DH, things seem to be getting significantly better. And yes, I know the answer. Something like 0.66 is about right. So if I go up to that, I get an R squared of 0.87, something like that. That's not a bad correlation. Just by doing all these probe molecules down a single column containing our test polymer, we can get a pretty good estimate of the DD, DP and DH of polycaprolactone. and from other evidence we know these are pretty good values. Importantly, recent work, especially at Ad Scientist, have shown that this works very well with things like excipients used in cosmetics and pharma. So this is a powerful way of getting at these important values, and is another illustration of how versatile and powerful IGC is. That's the end of the 4 videos. I hope this has given you a feel for what IGC might be able to do for you.